decided to hold this talk in English because I'm very involved in the project. Everyone else is from an English-speaking country, and all the terminology is in English. So if I would give the talk in German, it would be also quite heavy in English words. Also, my German is from Austria, and you might have problems understanding me. So I'm switching to English and hope that this is all right. As was said, my name is Entinger. I'm the owner of LXRobotics. It's a small consulting company based in Austria that is focusing on providing reliable real-time control and communication for robotic systems. The presentation is structured as follows. There will be a theoretical introduction where we'll be covering the main principles of the CyPhal protocol, take a look at its data structure description language, the currently supported transport layers, the minimum message and service set required to implement a fully CyPhal compliant node, the motivation behind the CyPhal protocol, adopters, users and use cases, and finally, in the second part of the presentation, I'll give a short practical demonstration of the CyPhal protocol. Let's jump ahead in the theoretical introduction, going to the main principles. A CyPhal network is a decentralized peer network. Decentralized means that there's no need for a central master node. Any node can be both a client and a server. All nodes are of equal rank. None is more or less important than another node. In CyPhal network, each CyPhal node has a unique numeric identifier. A numeric node identifier has a value between 0 and a transport-specific upper bound. The transport-specific upper bound is 2 to the power of 7 minus 1 for a CAN-based CyPhal network, and 2 to the power of 16 minus 1 for a UDP-based CyPhal network. That means that in a CAN-based CyPhal network you can have up to 128 CyPhal nodes, and in a UDP-based CyPhal network you can, in theory, have up to 6,536 CyPhal nodes. I want to stress again that there's no priority attached to the value of the node whatsoever. I already have told you CAN is a supported physical layer, and we all know that CAN does have built-in priority, but that's not part for the CyPhal protocol. In CyPhal, nodes exchange data via message publication and service invocation. Message publication is the primary method of data exchange for a CyPhal network and implements publish, subscribe semantics. One node is publishing messages, and 0, 1 or many nodes are subscribing to those messages. A message is identified by a unique subject ID. The purpose of the subject ID is to indicate how the raw data received from the transport layer should be interpreted. CyPhal subject IDs can be likened to ROS topic names insofar that they have the same purpose of identifying and matching specific message types. A CyPhal subject ID has a numeric value between 0 and 2 to the power of 13 minus 1. That means you can have a total of 8,192 CyPhal subjects messages in a given CyPhal network. Any of those subject IDs can be used, except a few that are reserved for special network functions, such as the heartbeat message. A service invocation is a two-step data exchange between a client and a service node and implements remote procedure call semantics. It is started by a client sending a service request to a server, the server then performing computations or taking actions, and then sending its response measures to the client. Service request and response messages, sorry, there are so many G words inside. Service request and response messages are identified by a unique service ID. Service IDs are quite similar to subject IDs. Again, they indicate how the raw data received from the transport layer should be interpreted. They are a numeric value between 0 and 2 to the power of 9 minus 1, which means we can have up to 512 services in a CyPhal network. And any of those service IDs can be used, except a few that are reserved for special network functions, for example, for the register access service, which we'll see in the second part of the presentation. Let's take a look at Cyphal's data structure description language. The data structure description language is a domain-specific language for defining composite data types. Composite data types consist of one or multiple primitive data types and can reference other data type definitions. DSTL data type definitions are contained in a UTF-8 encoded text file with the file extension .dsdl. They are versions and they may have a fixed port ID, but they do not need to have. A port ID translates to a subject ID in case of a message and to a service ID in case of a service definition. Here I'm showing you the structure of the 7509 heartbeat message. The heartbeat message is one that has a fixed port ID assigned because it's one of the special network functions. The heartbeat message ID is 7509, followed by the message short name, the version number, major and minor version, and the .dsdl file extension. Let's take a look at an example for a message DSDL data type definition. On this slide, I have represented a shortened excerpt of the 7509 heartbeat 10 DSDL message. At first glance, it's obvious that there are both primitive data types and composite data types included. Max application period, offline timeout, uptime, and vendor-specific status code are all primitive message types because they use the primitive built-in types, various unsigned integers varying from 8 to 32 bits length. Health and mode, on the other hand, are composite data types that refer to a data type definition that's stored outside of the 7509 heartbeat message. For example, I'm representing the mode 10 message below. You can see it is a primitive data type called value, which is a 3-bit wide unsigned integer, and various constant attributes that give semantic meaning to the numeric value of this value. This touches another point. Uptime, health mode, vendor-specific status code are all so-called field attributes. Field attributes mean that can change in runtime. They contain the meat of the message. They contain the data you want to transfer. There are also constants like max application period or offline timeout, or below here operational, installation, and so on and so forth, that are constant data types. Those are not transferred over the wire, but they are part of the data type definition. Here we see an example for a service DSDL data type definition. It's obvious on first glance that it's somewhat different from the message definition because it's split in the middle by 3 minus symbols. The upper part describes the layout and structure of the service request message, while the lower part describes the structure and layout of the service response message. In the request message, we see 2 field attributes called command and parameter, and various constants that define possible semantic meanings for various supported commands. You can also see that you can attach parameters to the command request message. This is a uint8 array. It's interesting to note that the maximum length of the parameter array is encoded by referencing a constant defined in another Cyphal DSDL data type definition file. This should give you some ideas about the power of composability and usage of the Cyphal protocol. The response message basically contains a status code that encodes the successful or not successful feedback information on the execution of the command with several predefined status messages. I've taken this example again from one of the reserved network functions 435 execute command 10. We'll be also using that afterwards in the practical demonstration. See how it works. Regulated data types include standard and domain-specific data types. Semantically, one can think of the regulated DSDL definitions as a standard set to use or as base building blocks for defining your own composite data types. At the moment, there's only one domain-specific public definition available, which is the Cyphal drone application layer, or UDRAL in short. All regulated DSDL definitions can be found on the OpenCyphal GitHub organization within the public regulated data types repository. Using a command line tool called Nunavut Generator, or NNVG for short, any DSDL data type definition can be transpiled into a C, C++ header or a Python package. The generated C or C++ headers or the Python packages contain function for serialization and deserialization, basically turning the field attributes of a Cyphal message or service into a byte stream for sending via the transport layer. The HTML target is not for serialization and deserialization, it's for documentation, for generating documentation. A conformance with MISRA and AUTOSAR of the generated header files is an objective of the Cyphal project. And we are nearly there. We are not fully MISRA and AUTOSAR compliant, but on the way. Let's take a look at the supported transport layers. Currently, there exist Cyphal implementations for CAN and CAN flexible data rate networks. For UDP-based networks, here we are targeting basically Ethernet, time-based T1S, time-sensitive networking, and related real-time Ethernet field buses. And there exists experimental implementation for serial raw byte-level links, like a real serial or like a TCP/IP socket. Open source libraries called libcanart, libudpart, and libserad exist that provide the Cyphal protocol implementation for the respective physical transport layer. All of those libraries are fully MISRA-C compliant and licensed under the permissive MIT license, meaning that you can basically use it in a commercial project without having to have any of the usual open source fears like copyleft attribution and so on and so forth. It's worth noting that libudpart, targeting UDP, basically Ethernet as a transport layer, works on any abstraction that's similar to Berkeley sockets. The purpose of these libraries, libcanart, libudpart, and libserad, is to convert the serialized byte stream that is basically containing the serialized message field attributes into an appropriate transport layer representation. For example, into CAN frames or into UDP packages. The reverse purpose holds also true. The libraries convert the transport layer representation back into a byte stream for deserialization. Let's take a look at the minimum message and service set required to implement a fully Cyphal compliant node. First of all, there's the heartbeat message that needs to be sent at least once per second. The heartbeat message, as you may remember from looking at this DSDL data type definition, contains information on node uptime, node mode, and node health. That's also the vendor-specific status code, but let's drop that for now. Furthermore, a Cyphal compliant node needs to implement the node information service, which provides runtime static, no specific information on request, such as the supported Cyphal protocol version, the node's hardware and software version, a software revision ID, this can be a Git hash for the node, a unique ID, usually derived from the unique chip ID that every microcontroller has burned in, a node name, and a couple of other parameters. This node information service is created by tools like Yakut and Yukon. Yakut is like the Swiss Army knife for Cyphal. We'll be using it later in the demonstration. The register interface allows the parameterization and configuration of a Cyphal node and is an important part of the protocol. A register is identified by a unique name and has a scalar or array value, which can be a string, a bit, various signed and unsigned integers of various length, and various length floating point data types. A register can be read-only or read-write, and it can be stored persistently or in volatile storage. In order to access the register API, you need to implement a register list access service. There are actually two services, 385 list10 and 384 access. The first one is used to obtain a list of all Cyphal registers, and the second one is used to read from a register or to write to a register. Finally, there's the subject service list, which needs to be sent at least once per 10 seconds and contains information on the subscribed and published messages of a node, as well as on the consumed and provided services. This one is mainly used for network introspection and diagnostics. If you've been following this presentation attentively so far, you're likely wondering, why would I want to use Cyphal? From what I hear, it sounds like just yet another publish-subscribe framework. It's a valid question. There may be different answers, but for me, the reason for involving myself in the Cyphal project and using the Cyphal protocol is that Cyphal basically is a fully powered DDS system for deeply embedded target firsts, and is now evolving up to integrate with modern robotic systems. DDS is the acronym for Data Distribution Service. Basically, it denotes a middleware for real-time and scalable communication between distributed systems. It's like a general overview name. So ROS, for example, is also using DDS systems to communicate the data. But DDS systems historically were meant to convey computers, fully powered application computers, running in a wide area or local area network. Cyphal, on the other hand, is an evolution from the UAV-CAN protocol and has been built from the very start for deeply embedded target firsts, memory constraints, computing constraints, 8-bit microcontrollers, and still offers all the features of a fully powered data distribution service system. Well, let's take a look at adopters, users, and use cases of the Cyphal protocol. On the right, you can see the Amazon Prime Air Drone Mark 30, and the Amazon Prime Air Drone is using the Cyphal protocol inside the drone for communicating with the various subsystems. Amazon is also an active contributor to the Cyphal project and is devoting some manpower helping maintain and developing it. NXP is also offering a couple of reference boards providing Cyphal implementations, but the logo guidelines of both Amazon and NXP are tricky, so I did not put them on the slide for fear of being targeted by their legal department. In my company, we have a project that is under development. It's a mixed electric hydraulic hexapod robot for search and rescue applications. It contains a lot of hardware, and all those hardware needs to be networked in some way. It is, we have basically many Cyphal enabled network devices inside. We've got the servo controller for controlling the hydraulic valves. We've got 2 hydraulic pressure sensors, 1 hydraulic pump, a radiation sensor, general aero controller, and actually 6 leg controllers that gather angles of the joints. And all those data is exchanged using Cyphal on top of CAN between the various Cyphal devices and a central single board computer. This leads us to the practical demonstration part of the talk, describing the hardware setup. RP2040 seems to be really popular in this track today because the first speaker also had an RP2040 based system set up here. I also brought one, a Cyphal Pico based stroke CAN board. It's an RP2040 based open hardware reference design with a fully Cyphal compliant open source firmware license under the permissive MIT license written by myself. And there's basically a USB CAN adapter that is also conveniently powering the board. Okay, I'll make this a bit bigger. I'll first call a setup script that is preparing everything for me, initializing the CAN adapter for 250 kilobits per second. Let's open a second window and dump the content of the CAN 0 bus on the bash so we can see if something's happening. I'm now connecting the board with the CAN. It will be supplied with power and hopefully come online. This looks good. We are seeing the heartbeat signal being sent once per second by the Cyphal Pico based CAN board. This massive amount of data that was just dropped is the subject service ID list that's sent once per each 10 seconds. I'm starting the Swiss Army knife of the Cyphal network. It's called Yakut with the monitor. And this is giving me already a plethora of information on the Cyphal network. First of all, I'm seeing here node ID, mode, health, vendor-specific status code, uptime. This information is all gleaned from the heartbeat message. So you see the node ID of I flashed this before I started the presentation, of a freshly flashed board is 0. It's operational. The health is nominal, and the uptime is now approaching 1 minute. Then all the parts that you can see over here come from the node information service. As soon as the Yakut tool is recognizing a new Cyphal network coming online, it is starting a node information. It's a request to the device, and then comes the supported protocol version, hardware version, software version with Git hash, and the unique chip ID, so a unique ID that's usually derived from the unique chip ID from my controller, as well as the name of the board. You can see that there's actually a second system being online, and this is the tool itself is opening and operating its own Cyphal node on my PC over here. We've mentioned the register API, which is used for parameterizing and configuring a Cyphal node. And using the Yakut register list node 0, I'm getting a list of all the available registers of this specific node. You may notice that here, for example, is a register that's called cyphal.nodeID. And if I am reading it, it agrees that the node ID of the Cyphal device is 0. Let's set the node ID to 10. It is now 10, but if we look into the monitor too, we'll be noticing the node ID is still 0. Why? Because the Cyphal workflow is usually you do the register configuration, then you store the data into persistent memory, and then you restart the node. So the configuration is not taking immediate effect. This can be done using the execute command message that we've seen earlier to the DSDL data type file by typing command 0 store. We are seeing a timeout error here, but I wouldn't be concerned about that. The problem is that the persistent storage on this device is a I2C connected EEPROM with 400 kilohertz, and the timeout is simply too narrow for the device to store all the data. Nonetheless, the device has stored all the data. Using the restart command, we trigger a restart of the device. And if we now take a look into the monitor tool, we see that the node has come back up under the node ID 10. Now, let's take a look at what else we can do.
So a node is a service?
A node offers 0, 1 or many services and 0, 1 or many messages. And so far we've only worked with with special network functions that are mandatory for each node. Now we'll actually configure the system to give us some actual usable data. And what I want to show you is the analog input for that. So I have here a sliding potentiometer, I'm not sure if you can see it. And I've connected it to the analog input of the board. And I'd be interested to know the content of the register Cyphal pub analog input 0.id, and I'm seeing it's 2 to the power of 16 minus 1. This is the default value and means that this publisher is currently not active. Let's give it a meaningful value of, for example, 100. You know the drill, we need to store the configuration and restart the node. Node 10 is back up, and you'll also see that the messages here have a new entry with the message ID 100. We've got also 7509, which is the heartbeat message, 7510, which is the subject service ID list. Here we've got the services. And now let's take a look and try and subscribe data from the newly opened publisher. In order to do this, we would like to know what kind of data type lies actually behind the analog publisher. And we can do this by reading the right register, which is the Cyphal pub unlock input 0 dot type. Whoops. We can see that the data type of this publisher is a UVCAM primitive scalar integer 16. So basically a signed integer of 16 bits value. Let's subscribe to it. A user could sub the subject message ID, then the subject data type ID, and I'd be interested in receiving metadata. You can see data sent once per second. This can also be configured. And if I move the slider along, you can see that the value is changing between 0 and 2 to the power of 10, because that's the ADC range that we have on this board. Let's take a look at another subscriber. Oops.
So the metadata is not transferred, it's what you measure.
The data is
Metadata.
so the metadata. No, the metadata is the things like timestamp, the source node ID, transfer ID.
Not transferred, it's what you measure or what you. It's not transferred over the wire.
Oh, it is. It is. So to be sure, the ADC is running on the Cyphal Pico-based CAN board, and I've got the CAN dongle talking to it. So this data is transferred over the wire. We also have a couple of digital inputs available. Let's configure one. We've got also, where is it? A digital input on the system that is currently set to default ID, so it's not publishing. Let's set this to 200, store the configuration, restart the node. And if we now look at the Swiss Army knife monitor output, we'll be seeing that there's a newly published message with the subject ID 200. Let's take a look again. What would be the type of the newly published message? We can see it is a scalar, basically a bit 10 that can transport the true and the false information. Let's subscribe to it. Message ID 200, bit 10 message. Again, we'd like to see metadata. And we can see the value is true because it's a pull-up. And if I press the button here, we can see the value changing to false. So this is a bit message. How are we in the time?
10 minutes ago.
10 minutes ago. Okay. Then we have time that I can also show it reverse. Now we have 2 times basically subscribed to message published. And now we will be sending a message from the PC to the board to control the system. There are 2 digital outputs available on the board. Let's take a look. Here they are. Let's configure it to a message ID of 300. Read it back. You know the drill. Store persistent data. Restart the node. Look at the Swiss Army knife. And you can see that the message IDs 100 and 200 show up immediately because the Yakut tool receives them and tracks it accordingly. But no one is publishing messages to the message ID 300 yet, which is why it took 10 seconds until the subject service ID was published for the message ID to show up here. Connected to the digital output, I've got a LED, and using Yakut publish message, I'm sending the value of true to the message ID 300, which is received and decoded by the board, which turns the LED on. With false, it can be turned off again. Now these are all very simple examples, but they should give you a basic idea what the Cypher protocol should be able to do. I'll open the monitor tool again so we can take a look at it. But this would be my presentation, my introduction to the Cypher protocol, and I'd be welcoming questions from you.